So, at the end of the last lecture, we tried to explain the conductance properties of electrons in metal, and we used the Druder model, which is a very simple model. The electrons are treated classically. We assume that they perform a random walk through the lattice. We assume that they are accelerated by the electric field and that they lose energy due to collisions with the ions. We had two parameters, tau to the -1, which is the rate of collisions, n is the density of electrons, and we ended up with an equation. J is the current density, which means that the conductance sigma is equal to density charge square times tau, the times between collisions, divided by n. Naively, we believe that E and M we know. There will turn out that we really don't know M, but let's leave it for the moment. And we should somehow characterize n and tau. And we said, well, if we measure just the conductance, it's not enough to pull out tau or n, we have to do an additional measurement. And the additional measurement that we will perform is the Hall effect. What is the Hall effect? It's just the influence of a magnetic field on the conductance of a sample. Before I start defining the geometry and what is exactly measured, I want to give a refresher of mechanics. Well, basically, you remember we started by the simple definition of what is current: density times charge times average velocity. We had, of course, a minus, and I'm rewriting it as function of momentum. I'm allowed to. Now,
it should be also an average of momentum, right?
Excuse me?
It should be also an average of momentum.
Yeah, but now I'm trying to look into it locally. So instead of the average, I'm talking about the velocity at some point, and I'm looking on the momentum at some point. What did I do here? I want to describe P at times t plus dt following the behavior at time t. I'm not sure that you've seen it in statistical mechanics, but this is the Boltzmann equation. So let's try to understand what's going on here. Okay, let's look on the first term. What does the first term say? If we multiply only by 1, or tau goes to infinity, so the momentum at time t plus dt is the momentum at time t, conservation of momentum. What does this term tell us? Well, if we have collisions, and we said that the collision just sets on average the value of momentum or velocity to 0, tells me that at each time dt proportional to the time of collisions, I lose part of my electrons that were in pt. Okay, so that's the meaning of this term. The second term tells me, well, I can lose electrons at pt, but I can also gain from where? Force that will accelerate the electrons that weren't at pt to pt. And that's all I'm writing here. Now I'll keep it up to order of dt. And now, yeah.
Can you explain that term again? The F,
Yes. P. What is the connection between P and F?
field?
Exactly. Derivative. That's all it says. Okay, where do I go from here? I want to write down a differential equation on P. And we'll write down the final form, and then I'll explain why I did these whole steps and didn't write just Newton's equations. Okay, I just subtracted that divided by dt. Okay, so if I had the regular Newton equations, I wouldn't have this term, right? derivative of v, and v is a derivative of x, so this is second derivative of x, which is ma. That's all that's written here. So this term, I would call it trivial. For some reason, this is less familiar.
And it's more general, right?
It's more general. To be true. This is a new term. What does this tell me? I'm living in a medium. Right? What is the difference between an electron that is accelerated in an electric field to an electron that is accelerated in an electric field in a metal?
Dissipation of energy.
Dissipation of energy. If I'm accelerating it in free space, it will accelerate forever, at least if I ignore relativistic corrections. On the other hand, if I'm in the metal, I'm accelerated, hitting the ions, losing the energy, continuing. And as we know, resistivity, one of its basic properties is that the resistor gets hot. Dissipation. And this just writes down the part of dissipation into our equations, into our equations of motion. So the whole exercise was to justify this term. If I would have written it immediately, you would stare at it and say, wow. Okay, now I have all the tools that are needed to understand the Hall effect. Let's first of all define what is the Hall effect. Okay, I take a long slab of metal and apply an electric field in the direction of x, call this x, and this y, and since I'm bad in drawing 3 dimensions, I do it in 2 dimensions, and I'll have a magnetic field B or H, whatever you're comfortable with, coming out. You remember the notation of the arrow. If I have a point, it's coming at us. Okay, so if I have here electron that is accelerated by the electric field, if I remember something of the Lorentz rule, and everyone will start to play with his hands and try to convince what is the direction. Not that it's very important at the moment, but of course the electron won't continue in a straight line. Will it gain energy? No, that should come out intuitively to you. Why?
Because magnetic force doesn't do work.
Yes, but give me something that you can explain to a 10th grader.
The force is perpendicular.
The force is perpendicular to the direction. of motion, and therefore you don't do work on it, because work is F times the direction of motion. You're not doing it. Okay, so this guy starts, depending on the strength of the magnetic field, it either starts to do a circle and gets himself hit on the edge, or if it's very strong, you start to do circles. Now, the picture that we built physically is that, and I remember which side is the plus, I think this is because you're diverting the current of the charge upwards, you'll have more direction of the charge is minus the direction. And you're getting more positive charge on the upper boundary than on the lower boundary. And what does that cause? Electric field or voltage. So although you started by applying only EX, you have also EY in the steady state of this problem. Okay, now we are left with, we have EX, EY, and the magnetic field. Of course, here it's HZ. And we just have to write down the equations of motions, but of motion, but before that, what are the two properties that I can measure? One is the conductance along the x direction, and the second, I'm in steady state, I don't have charges leaving the system, I have boundaries there, but I have either a voltage or an electric field in the y direction. These are the two properties that I'm able to measure here. So I stick a voltmeter here, stick an ampermeter here, and I go through the measurements. So, customary to denote rho h, or sometimes people are more pedantic, rho xx, applying the electric field in the x direction and measuring the current in x direction, which is and this is known as the Hall coefficient.
Just asking, I missed the part where you explained why we get a field from the UI and
Every, and let's ignore directions, every, let's say, negative, well, here it will be a positive current, goes to the left, right? So it's what is supposed to happen? All positive charge will move to the upper boundary. But from where does this metal at the end of the day is neutral, right? So from where do these charges come? They come from all over. right? So I'll have an imbalance, more negative charges on the lower part. Because it's a metal, all charge is sent to the boundary, right? So will it go on forever? All charge will run in this direction.
Why do we have this magnetic field? Due to the movement of the...
No. I brought it from home.
Okay.
It's an externally applied magnetic field. Why do I do it? Because I can. No, the real answer is I want additional parameters to measure in order to understand what are these coefficients here. So a very easy, relatively easy experiment is measure your conductance when you have also a magnetic field applied. And that's exactly what's the whole measurement, and until today it's a very, very important tool in determining properties of materials. It's so important that during the 80s, 1980, not 80, 2 Nobel Prizes were given for measurements of Hall conductance. That's the quantum Hall effect and the fractional quantum Hall effect. The quantum Hall effect tells you that there is some quantization of this property. Perhaps towards the end of this course I'll say something about it. If not, you'll hear about it in graduate school. And the most amazing thing is, under certain conditions, the electrons behave as fractional electrons. Can measure charges of a third, a fifth, and other rational denominators. And that was the second Nobel Prize. So basically these properties are relevant till today. Last year or two, you have the anomalous Hall effect that comes out because of the magnetic field of the electrons themselves, because they have spin, and that also creates something. That's a very hot topic, current hot topic. So this Hall effect was first measured, I think in 1879. It's still very interesting and current at the moment. Current, pun intended. Okay, so all of them are moved to the left, but at some point the imbalance in charge creates an electric field that's resisted. So you get into some equilibrium there. And this is a picture of the equilibrium. The charge wants to turn up because of the magnetic field, but is stopped from doing it because of the accumulation of charge on the boundaries. So, why did they define it this way? Go back 140 years. You could have written it in a different way, but that became the whole coefficient. Okay, so how I describe the behavior? Here I'm going back to this equation and writing down the components. This term is familiar to you from endless matriculation questions in physics. Every second matriculation has this equation in some form. But the new part here is okay, so I have to solve this equation. P has two components, Px and Py. We have Ex and Ey. And we have Hz. So one important thing, I'm always saying the word equilibrium. What happens in equilibrium?
Minimal energy.
Simpler.
There's no change in momentum.
No change in momentum. That's the meaning of equilibrium. When you say equilibrium, so any physical properties that we're interested in doesn't change. So, derivative of Px and derivative of Py are both 0. In the x direction, I have the x component here. In a moment, I'll define omega c. This is the cyclotron frequency. The frequency is that an electron revolves in a magnetic field. Comes out just from the definition. Okay. Let's multiply both equations by I use here? Use that. Okay, so it's just a multiplication by a constant and changing p times this term to j times tau. Okay? What else do I know?
So I have a question that there you wrote rho as a matrix, and now you're writing sigma as a scalar.
No, sigma is, if I want to be more precise, I'll write sigma x. This is the guy that I've defined here. I still haven't touched upon the whole conductance. In order to touch upon the whole conductance, I need another insight into the system. It's a trivial but important insight. What is the current density in the y direction?
Zero.
Zero, because I have boundaries there. It can't flow out of it. So, okay, now I have all the ingredients to write down the whole coefficient. So basically what I have here, EY just writing down what's written here. And since I need h here, I'll return omega c to its original definition. And so what's nice about the whole measurement? I go and measure basically the voltage in the y direction. I know the current and the magnetic field, and I come out with the density. So I can measure n independently and then plug in tau. Okay, so Hall performed those measurements, and he had two observations. Well, not really him, because he didn't know about electrons at all, so there weren't observations then. the density is not connected to the number of electrons in the valence band. So our simplistic picture has a problem. Simplistic picture has a much larger problem. We can get here a positive and negative value of the Hall coefficient, which means that the current carrying entities are either negative or positive. We started the whole story with electrons and ended up with an positron carrying current. As I said, it didn't bother Hall because he didn't knew about electrons at the time, but if you're taking Drude's picture seriously, this cannot be. So Drude is a very simple and nice model, and we'll see that it does capture something of the truth. But we don't understand what are the constituents of the charge-carrying entities, because their number doesn't fit a simple assumption that each atom contributes 1, 2, 3 according to its number of valence electrons carriers to the electron current. Second, it's not even electrons, it's something it could be, depends on the metal, something of positive charge. So we definitely need something else here. Okay, I'll talk a few minutes about another type of measurement that I can perform here. Okay, I measured conductance. I measure conductance in a magnetic field. What else can I measure?
Just temperature?
That's yes, but I'm not talking about it. Something even more basic in a sense. Also connected to conductance. Your wall socket. What type of current does it carry?
AC.
AC. All we talked about is DC currents. Why in the world would AC change anything in the behavior?
Because it's changing electric field.
Right, but I'm thinking about taking an electron in free space, put an AC. Well, you know that it will oscillate. Right? Put it in a media that can absorb energy, you can have lags between the oscillation and the energy dissipation. We know there are resonance of such properties. So putting an AC field can add another ingredient to our understanding. I won't go through all what it can contribute, but I'll start just by defining what we expect from the AC conductance to be out of the Drude formalism. We're using all the time Drude as a benchmark, as our zeroth approximation of the behavior of electrons. in order to further develop them further on. In principle, we could have different amplitudes at different frequencies. We will keep it one frequency here. Okay, the equations that we used already.
Shouldn't it be minus p over tau?
Yep.
Otherwise it's your rate can speed up.
Right. Okay, I'm looking on a solution that has also a frequency component of P. So I'm putting it here. Okay, just moved it from the right hand to the left hand and divided by 1 over tau minus I omega. Okay, so what do we have here? Let's remind ourselves that J omega NeV. So what we have here is I just multiplied both sides by minus NE divided by N. Okay, so I get basically the dE conductance divided by 1 minus I omega tau, which is a very usual, which we have seen in other problems of physics. Well, all that is assuming that P still continues with following the same frequency, which, as long as the frequency is not too large and we didn't hit any resonance, is reasonable. So if you're looking on this thing, measuring the AC conductance actually gives me direct information of tau. And what is the meaning of the imaginary part here?
Well, there are two meanings.
Okay.
Number one, it changes the amplitude. You can see how it changes the amplitude.
Mm-hmm.
And number two, it changes the phase. It changes the phase in relation to.
Right, and I want to emphasize the second one. The first one is, in a sense, is more trivial. The second part is important because it tells you that the response of the current occurs later than the change in the field, which in a sense is very natural. It takes time to dump the motion in one direction once you changed the force in the other direction. And it depends also on the medium, how fast or slow you do it.
Yeah, really, it's normal because if you put tau to 0, you just get over I omega minus I omega, which is just when you get a normal harmonic oscillator.
Right. Exactly. It's a whole difference between a forced harmonic oscillator and this behavior is that you have a medium that dissipates. Okay, so we have the Drude behavior, and we're left with a lot of questions on what's carrying the current in this metal. Certainly not the simple electron picture. Okay, so what are we missing? We're missing the two things, actually. One, the electron is a quantum particle. Now, it means that all our equations of motions are not necessarily correct, Although this is not the biggest problem, because we know from Ehrenfest, on the average it's not too terrible, right? But there is another ingredient to the fact that electrons are quantum particles beyond the Schrödinger equation. That's actually something that is extremely important, and we tend to forget about. Okay, so when I'm looking on a single quantum particle, the fact that I'm obeying Schrödinger equation instead of regular mechanics makes some difference. But if I'm looking on an ensemble of many particles, there's another effect that comes into account, which is
Pauli exclusion.
Pauli exclusion. Actually, everything around us cannot be understood without Pauli exclusion. So we know all the chemistry of atoms comes from Pauli exclusion. Otherwise, why do I care about N, L, and M in the solutions of an electron orbit around the nucleus? All of them will be in N equal 1, L 0, M 0, and they all look the same.
And we need more and more higher temperatures. We fall to the lowest level.
Everything around us would be different. You wouldn't, instead of sitting up there, you would go through the material of the floor and continue to the core of the Earth. Nothing will stop you from going through. All the fact that any material has hardness avoids going through each other is also Pauli's exclusion. So that's one property. The other property is that we have a lattice. And this lattice plays a very important role in understanding the behavior of electrons. That will explain us why we have insulators and conductors. That will explain us basically why we can have negative or positive charge carriers. That will explain us basically why taking an insulator that we call semiconductor and putting a small number of impurities completely changes its behavior, which all our technology, electronic technology, is built on. So all of it has to do with the fact that we have a lattice. So, step after step, first thing, we'll put in quantum effects by taking into account Pauli's exclusion, but we'll forget for a moment about the fact that we are living in a lattice. Those electrons are living in a lattice. Okay, why? Because it makes life simpler, and at least part of our questions about Rude will be answered already there. Okay, so if I don't have a lattice and I have a piece of metals, what do the electrons see? You have to write a Schrödinger equation, right? That's write the Hamiltonian of the electrons. What is the simplest Hamiltonian that I can write down for electrons in a metal? Free. Exactly. I'm taking free electrons, ignoring the fact that I have ions and they have potentials and it's a periodic potential and so on and so forth. throw it out. The only things that I retain,
The kinetic energy.
kinetic energy and the fact that they are in a box. Well, those electrons, if I take a piece of metal, don't wander out. How do I explain they don't wander out? They're in a box. Physically, why are they in a box? Even if I forget the fact that there's a lattice there, there is still a background of positive charge, and if the electrons will wander far away, they'll be pulled back. So instead of writing a detailed potential that stops them from leaving the metal, I'm just saying they're in a box. Okay, infinite outside, zero inside. Infinite outside, zero inside, and that's that. Okay, so now we're back to quantum mechanics. The usual free electron Schrödinger equation. I put them in a box, and to make my life even simpler, I put in periodic boundary conditions. Okay, so basically, and the same for x and y. Okay, we know the solution, we have seen it. So V is the volume, square root, of course. Hope I'm not surprising anyone. Okay. Of course, kx or y or z, not any numbers because they're in Okay. Just in order to add a bit spice into the game, some of you have heard about two-dimensional metals or one-dimensional metal. Some of you haven't heard about it. Just a matter of fact, all your electronic devices are actually two-dimensional landscapes of what's happening in the chip there. But when I'm saying two or one-dimensional, what do I mean?
2D lattice.
Smaller than the wavelength of the electron.
Simple. If, let's say, I have LZ much, much smaller than LX and LY. So if NZ is equal 0, no large contribution. If NZ is equal 1, or a higher number, there's a huge contribution of energy here. Right? So if I'm looking on low energies, I will always have NZ equals 0 and whatever in NX and NY. Because to change NZ will cost me a huge amount of energy. Therefore, effectively, I can think about the system as a two-dimensional system, because only NX and NY changes, NZ is fixed to 0, unless I go to very high energies. So that's the meaning of a one-dimensional, two-dimensional, and then sometimes you just don't bother to write the fact that you have also an NZ component that is not in the game. Okay, so if I'm writing down Kx and Ky quantum numbers, basically I'll have here forth. So I have here a bunch of points in this space where I can have an electron occupying it or not occupying it. And so on and so forth. Now, when I fill up electrons, how do I fill them up?
From the lowest energy to the...
From the lowest to the highest, right? So I get here a circle. I'll fill up all the points within the circle, and I will leave empty all the points above the circle. What did I assume here?
Continuous.
This is not very continuous.
You need to count them in.
I'll count them. What do I assume here? That the temperature is very low. I don't have energy to waste on moving them out. If the temperature is extremely high, I'll fill up at random these points, and I don't care how much energy it costs me. The temperatures are low. If the temperature is low, then I'll be forced to fill up only points as close as possible to the origin. Because any time that I move further out of the origin costs me more energy. So, what is this circle called? Circle in 2-dimensional, ball in 3-dimensional.
Density of states.
No, density of states is is the number of states per unit volume.
Ah, the Fermi surface.
Fermi surface. And this is perhaps the most important parameter in order to understand the behavior of electrons in metals. We have to know how does this Fermi surface look like. For free electrons, it's a 2-dimensional circle to 3-dimensional sphere. But in a concrete lattice model, it could be very different, and we'll learn how to construct it. Okay, so what is the densities of these points in the K space? You have a point. Let's assume now for simplicity that Lx is equal to Ly equal to Z. You have one point for each volume unit of 2 pi over L to the third. Right, so the total number of points within a volume is the number So if I have n electrons, should be equal to the volume of the sphere divided by the number of points per unit volume, or the volume of each point there. And I forgot something. What is that? Spin. Exactly. Each point can have 2, so I have to add here 2. Assuming that I can collect all my pi's correctly, this is the number of electrons within the volume of a sphere of radius kf. Kf is a Fermi wave. Well, you can write it the other way around. What is K for me? If I know the number of electrons,
N is a...
N זה קריאה בשלישית.
density of electrons per unit. What else could be interesting? Of course, the Fermi energy. You remember that we used RS and A0 in one of the previous lectures, and I'll write this also down. Okay, what do these numbers tell me on typical metals? We remember, well, hopefully we remember, that RS is a few A0s. A0s is the Bohr radius, and RS is the typical distance between electrons. So basically, we have that the number of electrons that K for me is of order of 1 over an angstrom, more or less. Well, not surprising, everything in these systems in units of length is of order of an angstrom or a few angstroms. This is, truth be said, somewhat surprising, but not really surprising. So this is larger than 1 squared, tens of electron volts is a typical scale of the Fermi energy. Why am I saying it's not surprising? What is the scale of the ionization energy of the hydrogen atom?
13.6.
Around 10 electron volt. You're right, it's 13.6, but for our... So it's in the same ballpark. So we stop a minute and think. Basically, the Fermi energy is of the same scale. The energy of the highest most filled state is somewhere on the verge of the ionization energy of a hydrogen atom. Now, perhaps a number that will surprise you. Electrons in Fermi energy are quite fast. 10 to the 6 meter per second. That's fast. Still not relativistic, 2 orders of magnitude, but quite fast. Okay, what else can we pull out of this model? You remember that I asked the question about heat capacity. If I have half kT per electrons per degree of freedom, I have a lot of energy in inside that contribute to the heat capacity of the solid. Okay, let's first of all see the ground state energy. Right, I have to sum up on the energy of each point here, as long as it's smaller than K Fermi. I don't like summing up. If L is big, instead of summing up, I can integrate. So, should really write down. Where is it? 2 pi. Okay. So these guys give me the traditional 4 pi.
Right, with the sign, right?
I had just an integration of the angulars that gave me 4 pi, and the k, which gives me a contribution of dk is k squared times k, so it's an integration over k to the 4th.
פה זה בלי אינטגרציה כאילו.
Here I'm only taking the norm k component. I already pulled out the 4 pi here. That's why I have only pi squared. Okay, we stare at it and it means nothing to us, right? But let me write it down in a different form. Ground state energy per particle.
איך נהיה פה K ברגעית באינטגרל?
מה,
K ברגעית בסדר. יש לי זה, יש לי.
Okay? The dangers of living in 3 dimensions. Okay, and you remember that we defined n in this form. Okay, and this intuitively makes some sense. We have guys here with a small energy, we have here guys with a larger energy. We have more states close to the boundaries than in the middle, therefore it's not half E for me, it's a higher proportion. So, we have the ground state. How does that help us to understand heat capacity, which we'll do in the next lecture. Let's do heat capacity qualitatively. Classically, what do I do there? I change the energy per degree of freedom by moving from KT to KT plus something, right? Now, let's look what happens here. This guy, I want to give him a bit more energy. So what does he tell me? Sorry, I can't use it. Because that will move him to the, let's say, to the next position, but it's occupied. Pauli's principle. I don't have what to do with this energy. So, if I'm changing the temperature by a bit, all the bulk, all the middle sections of the electron occupation says thank you, but no thank you. I can't receive any more energy. Who's in the game? Only the small fraction on the boundary, on the sphere. So the number of electrons that take part in the game is much smaller than the total number of electrons. Therefore, just because of the Pauli principle, not all the electrons, only a small fraction of them are in the game and contributing to heat capacitance. I'll tell you a secret which needs a bit more of work, but with it. If I'm looking on conductance, what happens in conductance? I add an energy proportional to the voltage, but conductance is small voltage. How the current changes with changing the voltage by a bit. So I'm trying to move the circle somewhere to the right. Why to the right? Because I add energy in some direction. I change K in some direction. Most electrons tell me, sorry, I can't accept it. I don't have what to do with it. Only the guys that are on the boundary are playing. So the number of electrons which we were surprised doesn't fit the number of valence electrons. Again, makes sense. And that's just the Pauli exclusion, nothing more. Can't be understood for classical, makes a lot of sense if we're dealing with quantum particles that follow the Pauli exclusion principle. Okay, so we'll continue in the next lecture.
Thank you very much.
יש לי כמה שאלות, קצת מעניין. קודם כל, זה לא נחשב בבעיה הזאת, אין פה אלקטרונים שצריך.
זה מה שאמרתי.
נכון. אמרנו שרק אלה יכולים לזוז, אז זה כאילו שכבת הוולנס.
לא. זה האפקטיב שכבה של הוולנס. כל אלו הם אטומי